There is a lot of confusion around quantum mechanics, and I think a solid part of it comes from how it's often oversimplified in the popular science.
The quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble.
The observer effect is usually presented as something mysterious or even mystic, but in the fact is just a piece of common sense. And today I'm going to clear this up. The same goes for the Heisenberg uncertainty principle. It's not some spooky quantum magic. Give me a few minutes and I'll show it's surprisingly obvious. Let's rewind to early 1927. Heisenberg, Bohr and Schrödinger were exhausted trying to figure out how the quantum mechanics actually should look like. Sure, Schrödinger has already written his famous wave equation, and it surprisingly good describes the hydrogen atom, but quantum theory as a complete consistent framework wasn't yet done. Two key ideas were still missing, the ideas the scientists were already playing with but hadn't fully worked out or published. Bohr was working on what would become his principle of complementarity, and Heisenberg was developing something that's the focus of this video, the uncertainty principle. It's the idea that we can't know both the position and the velocity of a particle at the same time. The uncertainty principle. What's up with that? In the late February 1927, Heisenberg wrote a 14-page manuscript and sent it to Wolfgang Pauli. Pauli loved it, and just a few weeks later the manuscript was submitted to German physics journal Zeitschrift für Physik. At that point, quantum mechanics existed in pieces, but it was still missing some foundational principles. The uncertainty principle filled a big part of that puzzle. Let's break it down. One of the simplest waves we know is a plane wave. It spreads out infinitely, so it's completely not localized. In the fact, a lot of classical electrodynamics is based around this plane wave. And it gives quite fruitful answers. But it's barely applicable for quantum mechanics because we cannot describe a particle by a completely non-localized wave. Now, if we say a particle has wave-like properties, we cannot apply the most developed wave to this particle. The particle cannot be everywhere, it simply doesn't make any sense. So we have to use something as a wave packet, which is localized in space. That's the place where the things start to get interesting. But how do we measure how local the packet is? There is a twist. Putting a slit in the path of the wave doesn't just block a part of it, it actually changes it. The effect is known as a diffraction. Now the edges of the slit emitting a spherical waves which interfere with the original ones. And when the size of the slit becomes comparable to the wavelength of the wave, the diffraction effect becomes the dominant one. So the very act of measuring where the wave is changes it, and it brings us straight to the uncertainty principle. Let's go deeper. What if I want to see an electron under a microscope? I need light, the photons to bounce off the electron. But there is a catch, the photons has some limited size, it's actually limited by its wavelength. And I just cannot resolve anything smaller than its wavelength. To get a better resolution we need a shorter wavelength, but the shorter wavelengths carry more momentum. When the photons bounce off the electron, they transfer some momentum. Shorter wavelengths, bigger momentum, and the bigger perturbation in the momentum of the electron. And vice versa. If I want to disturb the momentum less, I have to use a longer wavelength. Then I disturb the momentum fewer, but I worse the resolution. This trade-off is exactly what Heisenberg was thinking about. Later this was formalized by the quantum mechanics and statistical physics. There is a fundamental limitation how precisely simultaneously we can find a position and momentum of an object, any object. There is a minimal cell size in the phase space, and we cannot overcome it. There is a minimal cell of uncertainty. Please like this video, my channel is very small and needs your support. But is the uncertainty unique for the quantum mechanics? Not really. It appears whenever two quantities are related by the Fourier transform. It works, for example, for sound or any classical wave. The shorter pulse in time we have, the less sure what wavelength we are. So the uncertainty itself is not weird quantum-only thing. It's just how waves work. And quantum object behaves like a wave. The point is, the uncertainty principle doesn't come from a fancy math. Yeah, it's described by a fancy, interesting math well. Nevertheless, it can be explained in our daily simple terms. and the core idea is physical and intuitive. Every time we want to measure something in quantum system, we have to interact with it, and the fact of interaction disturbs the system. That's what people call the observer effect. And it's not unique to quantum physics, we see it in our daily life too. For example, if I want to measure resistance, I'm adding my voltmeter to the circuit, I am modifying the circuit. Even though it has a high resistance, some current flows through, and this perturbation can matter in the small systems. Or in the case we want to have the result with a high quality. Or another example, if you want to measure the object with a ruler, when you measure, you touch it, you scratch it, you leave your fingerprints, so the object before and after is actually not the same object. It's changed. So yeah, in the quantum physics, the observer effect is exactly this kind of interaction. It's just more obvious and more dominant compared to our daily life, our microscopic scales. And that's the whole point. It's not mysterious, it's not mystic, it's quite obvious, simple and straightforward. And this simple fact leads us to two huge concepts in all quantum physics, the uncertainty principle and the observer effect. If you've made this far, thank you for sticking with me. I hope it made some sense and even cleared up some myths. If you have questions or thoughts, please write them into the comments. I would love to hear it from you. And if you enjoy this, please consider give the video a like and probably subscribe my channel if you want more videos like this. Your support means a lot for my small channel. Thanks again and see you in the next videos.